you're going to be our third speaker. Yeah, and it is 10 o'clock. And so I'll give a quick intro and we'll jump right into everything. So welcome everyone to the Locomotion 2 Podium Session. I'm Jaimie Roper. I'm an assistant professor at Auburn University, and I'm joined by my co-moderators, Dr. Nidhi Seethapathi, who's a postdoc right now at University of Pennsylvania, but she's going to be starting as an assistant professor at MIT in January 2022, so congrats. And I'm also joined by Dr. Caroline Klitza, who's an assistant professor at the University of Nebraska, Omaha. So thank you both for being here. And we'll have 12 speakers. So just like all the other podiums you've been to, if you haven't been to one yet, welcome. So 12 speakers, each gets 5 minutes on their presentation. And after the fourth speaker, we have time for questions. You can submit your questions through the chat or feel free to raise your hand via Zoom, and we'll try to make sure each speaker gets a question. And of course, after that, we'll move to spatial chat for further discussion. So on that note, thank you all for being here, and we'll get started with our first speaker, Loubna Baroudi from the University of Michigan. And Loubna's talk is entitled Contextualizing Walking Bouts in the Free Living Environment.
Thank you. All right. Okay. So I actually renamed it. So I'm Loubna Baroudi, and today I'm going to talk to you about contextualizing walking speed in the real world. So walking speed is a very important parameter. It is a strong predictor for different health outcomes. In the lab, we are able to make very accurate measurements of walking speed through motion capture, gait mats. However, the way I walk in the lab is probably not really representative of how I would walk in the real world. So researchers are turning towards data collection outside the lab, which has been made possible with the advancement in wearable sensors. Wearable sensors are compact, they can be worn for extended periods of time, and they allow us to collect data in the real world. However, in both of these contexts, people extract values of walking speed and they aggregate them into one value, mean walking speed. Outside the lab, it might not be the best way to go since there are so many different types of walk that are being performed. So context needs to be considered in the estimation of walking speed in the real world. So we could imagine a setup where I have a subject wearing an accelerometer, and then I ask them to carry their phone, so have GPS data, and when they go home, do self-reports. But this is not really realistic. This would be very burdensome, and I would have a lot of compliance issues. So this brings my research question. How can we contextualize walking speed, walking in the real world using a single point accelerometer? And then the second question is, what is the influence of context on walking speed? So I'm going to start with the contextualization. So the experimental setup is we have a thigh-worn accelerometer called the active PAL for 14 uninterrupted days, and the parameter that we extract is stride speed. So the first thing I want you to note is that walking in the real world is discontinuous. It's not like I'm in the lab walking in a straight line where there's no obstacles. No, walking in the real world has different durations and different continuity. I could be in my kitchen, stepping left and right. I could be outside with pedestrian lights and other people, or I could be in a park doing a long continuous walk. So the way we modeled these differences, this continuity problem, is through walking periods. So a walking period starts when walking is detected. When walking stops, we look at whether the person is sitting or standing. If they sit, we end the walking period. If they're standing, we look at whether they're standing for a long time. If yes, we end the walking period. Otherwise, we continue it until the walking stops again. So a walking period can look either with only walk in it, or it can contain standing periods. And the way we parameterized walking periods is using the duration, the continuity, and then each walking period is going to have a certain number of values of walking speed. The continuity is a percentage, with 0 being discontinuous and 100 being continuous, meaning without pauses. So we're going to see what is the influence of this contextualization on walking speed. So here we're looking at walking periods for one individual based on their continuity and their duration. And I want you to observe how when I subset modes based on continuity and duration, I get widely different estimates of stride speed. The first thing I want you to look at is average. My minimum stride speed is 0.95, and the biggest one is 1.42. That is a big difference if I want to be accurate in my estimation of walking speed. The other thing I want you to note is standard deviation. If I look at mode 1, where it's like short, interrupted periods of walking, I have a lot of standard deviation. Whereas if I look at more like long, continuous walks, my standard deviation is a lot smaller. So it might be mode 7 that is interesting for me if I want to extract a very accurate estimate of preferred stride speed. So overall, the important note is that walking speed varies with continuity and duration. So my contributions, if it wants to go to the other slide. Yep. My contributions are the contextualization of walking speed by coherently modeling the stop and go nature of real world walks, and the discovery that walking speed changes significantly with period duration and continuity. Thank you.
Thank you very much. All right, so our next speaker is Sadegh from Northern Arizona University, and her talk is entitled Real-Time Ankle Plantarflexor Moment Estimation Across Slope Walking and Uneven Terrain.
Hi, everybody. My name is Safoura Sadegh, you can call also Sarah. I'm presenting a real-time ankle plantarflexor moment estimation across different walking. Ankle joint is an important joint in human locomotion because of the vertical support and helping forward progression. And that's why the ankle joint is a frequent target for wearable robotics. A desirable control strategy for an ankle-assistive device needs to be adaptive to variable terrains, directly respond to the user input in real time, and effective for individuals with disabilities. Proportional myoelectric control strategy is one of the available control strategies which meets this criteria, but has some issues. One of them is the skin electro reliability challenges. It's difficult to implement outside the control environment of laboratories, and might not work for individuals with disability due to deficient muscle activities. We propose a proportional moment control strategy, and we hypothesize that it is adaptive to different terrains, reliable and robust, and beneficial for impaired populations. In this method, we use inverse dynamics approach. The inverse dynamics equation of ankle moment consists of three main terms. The first one is the angular acceleration times the mass of inertia of the foot. And you can see that the effect of that in the ankle moment is close to 0. And in the graph here, it's shown in the dashed line. Second term is the contribution of the tangential ground reaction force in the ankle moment, which you can see that in the purple graph here. And the effect of that is less than 3% in ankle moment. And finally, the normal ground reaction force has the most significant effect in the ankle moment with 97% contribution. And you can see that in the blue graph here. That's why for estimating the ankle moment, we use this term. The normal ground reaction force is mainly being applied to the foot from heel and forefoot. And if we assume foot as a beam rotating around the ankle, the heel causes a dorsiflexion reaction from the ankle joint to maintain the equilibrium. And the forefoot ground reaction force causes a plantarflexion reaction from the ankle. Because the goal of this study is to estimate the plantarflexion, we only use the ground reaction force applied to the forefoot, the normal value times its moment arm. Next, we need to estimate the relative value. So we can multiply that by the desired set point and apply through motors to our wearer. In order to estimate the relative ankle moment, we need to divide the estimated ankle moment by the maximum value of that during the baseline. This ratio, our study shows that this ratio is close to 1 because the moment arm of the normal ground reaction force applying to the forefoot is almost consistent during the gait cycle on different terrains. So we can come with the final equation of dividing the normal ground reaction force applied to the forefoot by its maximum to estimate the relative ankle moment. To record the normal ground reaction force in real time, we used a force resistive sensor under the forefoot of the wearer. We tested our results, our approach on level walking, incline up to 15-degree and decline walking. The accuracy of the model in level walking and accuracy in incline was about 97% with correlation coefficient close to 1. And in decline walking, the accuracy of this approach was 92% with correlation coefficient of 0.97. And in this graph, you can see that in incline and decline, still the contribution of the normal ground reaction force is the most significant contribution compared to the other terms. We have also tested our model and estimation on different uneven surfaces. We've tested this on walking on foam, walking on hardboard when the heel is on board and when the toe is on board. And we got 88% accuracy for walking on foam and 90% for walking on the board. And you can see that in this graph, how well this model can estimate the relative or normalized ankle moment in real time. Our future work is to test our model and approach on real-world overground testing and test it on individuals with disabilities to evaluate the performance of our model on different populations and on real-world different terrains. Thank you.
Thank you, Sarah. All right, our next speaker is going to be Ross Neuman, and he's from the University of Texas at Austin. His talk is entitled, "There are unique joint kinematics that exist during locomotor transitions from level walking to stairs that are affected by stair grade."
Thank you. And is it showing the presenter view or?
Yep, we see presenter view slides.
Okay. All right. That's good now. Okay.
Now we do see the note slide.
Oh, okay. Sorry. It usually starts out the other way. All right. Okay. So my name is Ross Neuman. I'm in Nicholas Fai's lab at University of Texas, and today I'm going to be talking about the fact that there are unique joint kinematics during the locomotor transitions from level walking to stair walking, and that these are also affected by the stair grade. So a little motivation for this kind of research would be in like device control. A lot of the time, like this is an example of like a hierarchical control scheme where you're continuously evaluating kind of these various stance and swing profiles and trying to sense whenever somebody's switching to a different sort of terrain so that it can intuitively change rather than somebody having to select when they're going to change. However, typically this kind of thing will go straight from, say, walking to stair mode or walking to ramp mode. But there's no specific mode built in for transitioning. So I wanted to look at locomotor transitions and see whether a more continuous adaptive kind of thing would be better than these hard-coded states. So basically we're asking, are these transition kinematics anything special? So here is just an example of ankle angle. So this is level walking. This is the transition stride into walking downstairs. And then this is stair walking here. And so you can kind of see that, you know, the beginning of the level walk looks like the beginning of the transition stride looks like level walking. The end of the transition stride looks like the stair walking. Makes sense because it's transitioning from level to stair walking. But is there anything more going on here? So in order to do this, we did an experiment with 10 subjects. We used an incline adjustable 5-step staircase at 20, 25, 30, and 35 degrees. And we looked at the transition strides as far as this study is concerned are just the leading leg ones. So basically when you transition onto walking stairs, this is the step that initial heel strike is on the ground and subsequent heel strike is going to be on the very first step. So it's a little bit different than like the trailing leg transition stride, which is going to be ascending the same height as like regular stair walking. This is the one that only, you know, ascends the height of a single stair. And so we use statistical parametric mapping so that we could do statistical tests across the entire stride rather than individual points. And so I'll have some slides to dig into this a little more and show it a little better, but basically this kind of gives an overview of all the things we're looking at. So we have the various inclines for ankle, knee, and hip angles, both the transitions from walking to stair ascent and the transitions from walking to stair descent. And then the results from the, so what we did was look at transition, level walking, and stair walking at each of these and compare them. So that's what these 3 different trajectories are for each one. And the shaded regions indicate where there are significant differences between transition strides and level walking and transition strides and stair walking, and areas where they overlap would indicate that they're unique kinematics. So if we look at this, this is the same thing that was in the other graph, but it's now, you know, you can actually look at the trajectories. So basically, you can kind of see that in the beginning, like in the stance phase, a lot of the time the transition strides are different from the stair walking. And then in the end, they're different from the level walking, which makes sense. However, importantly, you see that there's a lot of these areas where there's the overlap, oftentimes in early swing. And we can look at the stair descent as well. And so this is showing us that basically these transition strides are not simply, you know, cutting off from level walking and then turning into stair walking. There's some, you know, additional unique kinematics going on. And so especially for the stair descent transitions like this, it's a very dangerous time to trip because you have stairs to fall down. And so for designing devices, this is an important thing to look at. Also for just the straight up effects of stair incline, these shaded regions indicate areas where the incline itself was influencing kinematics. So you can see that in steady state stair walking, there's a lot of effects of incline generally with just like the, you know, angle reached. But you can see that in the walk to stair transitions, particularly descending, there are still some effects from the incline. So basically this study was to quantify the uniqueness in the lower limb joint kinematics during the transitions from level walking to stair ascent and descent, and where and to what degree did these happen. So this adds to our basic understanding of human locomotion, could potentially help with identifying fall risk and possibly have applications into device control. Thank you.
Thank you, Ross. And our final speaker before our Q&A will be Heidi Fehr from the University of Wisconsin-Madison. And her talk is entitled The Effect of Walking Speed, Slopes, and Stairs on Dynamic Mean Ankle Moment Arm.
Oh, sorry.
Hello.
Hello, everyone. My name is Heidi Fehr, and I'm a PhD student at the Badger Lab at the University of Wisconsin-Madison. Today, I'm going to be talking about how dynamic mean ankle moment arm changes with walking speeds, slopes, and stairs. So to give a little background, I'm going to talk about prosthetic feet. So prosthetic feet can be categorized into three main types. There's passive. These have no electronic components and essentially work as a spring damper system. Based on their design, they have a fixed stiffness that can adapt to different walking conditions, such as walking on ramps or stairs. There are also active prostheses, which are fully robotic and have the ability to provide mechanical power during the gait cycle, such as during push-off. These usually offer some adaptation to different terrains, and they can adapt all throughout the gait cycle. What I'm focusing on today, though, are semi-active prostheses. In order to have a lowered complexity and weight, these prostheses only adjust once per stride. For example, here in the middle, we have the variable stiffness foot, and it adjusts its stiffness once per stride when the foot is in the air. So it has a little fulcrum here with the white square, and this moves either forward or back to make the foot more or less compliant. So if we wanted to control a semi-active prosthesis such as this one to adapt to different terrains, we'd have to select an appropriate target metric. In this study, we're exploring the dynamic mean ankle moment arm, or DMAMA measure. DMAMA is a single number per stride that describes how the ankle controls the location of force interaction. In its calculation, we can see that it's driven by the angular impulse about the ankle, which is influenced by things such as the amount of time that the foot is in contact with the ground, like walking speed, and how high the forces are during this time. This can give you an idea that if the walk is very bouncy or very smooth. This is then normalized by the impulse of the sagittal ground reaction force. Functionally, we calculated this quite simply by dividing the mean ankle moment arm by the mean sagittal ground reaction force. And the result is a single value per stride. I want to highlight that this is pretty important because, like I said, we had a variable stiffness foot that only changes once per stride. So we need a measure that's only once per stride. So in our previous work, we actually took the VSF and looked at how DMAMA would change with different stiffness settings and over different ground inclines in transtibial amputees. What we saw was that, yes, changing the stiffness and ground incline did influence DMAMA, and it increased with both stiffness and ground incline. This leads us to the motivation for the study I'm talking about today. If we were to actively try to control DMAMA, what value would we set it to? To find this out, we asked, how does DMAMA change in unimpaired people? Using motion capture and embedded force plates, we observed the gait in 10 unimpaired individuals as they either walked over level ground at different speeds, slow, normal, or fast, and as they ascended and descended a 5-degree incline at a normal self-selected walking speed, and as they ascended and descended stairs also at a normal self-selected walking speed. Here's what we found out. When walking over different speeds, we saw DMAMA decrease as walking speed increased. That is, the moment arm moved towards the heel as walking speed increased. When walking on ramps, DMAMA moved forward as ground incline increased, suggesting a more four-footed walk. In stairs, when going downstairs, DMAMA was significantly higher. We can kind of imagine this because when you walk downstairs, you kind of go toe first. DMAMA was lower when going upstairs. Moving forward, we're looking to combine this with what we've learned in our previous work to test and implement a biomimetic control law. Like I mentioned previously, our work observed changes in DMAMA over different terrains and forefoot stiffness when wearing the VSF. Combining that with the findings of this study, we can get an idea of a control law. This graph here shows the degree to which we think we should change the stiffness in the VSF as ground incline increases in order to match unimpaired biomechanics. In the future work, we'd like to implement this control law and see if it actually improves the user's experience. So some of our key takeaways were that DMAMA is in fact sensitive to walking speed, ground slope, and stair ambulation in unimpaired individuals, and that DMAMA is a promising measure to control semi-active prostheses, especially ones that only adjust once per stride. So, thank you.
Thank you, Heidi. All right, so now I'll turn it over to my co-moderators, Nidhi and Caroline, for some questions.
Great. So our first question, I'm going to ask for, Loubna's been getting questions in the chat, but Loubna, can you answer the question about by Peter Adamczyk, which is, Do you have any information to understand the environmental context with the different regions of the duration versus continuity graph?
So in our experiment, we only have an accelerometer, so we have no information on what is happening around the individual. I think it would be great if we could validate whether some contexts match with some of the areas of the continuity duration graph, but it was not done in this study. We wanted to do like the simplest possible setup and see whether we could see some sort of evolution in walking speed based on the contextualization that we did.
Okay, cool. Thanks. Let me ask now a question for Ross. This is from Peter as well. Have you attempted to write a continuous function mapping incline of the stairs and time with swing to joint angles?
Yeah, so I have not personally worked on that, but some of the people we worked on gathering this data with are in the process of doing that kind of thing. I was hoping to see, when I was looking at the transition kinematics, I was hoping to see a little bit more of a continuous kind of change in the regions of significance between as you went up the angles, but that didn't end up. It jumped around a little bit. However, but yeah, it does look like you could probably put a pretty, fit a smooth surface to the kinematics through inclines.
Cool. Thanks. Okay, I'm gonna ask now a question for Heidi. Why do you think the d-mama decreased with faster walking? It seems like the ankle moment would increase with faster speed. So why would the moment arm decrease?
Yeah, so what we saw was that when running, well, this is in previous work, we saw that when running, d-mama increased, but when walking faster, it decreased. This was counterintuitive, but we think this has to do with, since you're walking, it's also your ankle trying to stop you from going too fast. And so this is why we think that the moment arm is decreasing.
Okay, cool. Any more questions? Did I miss any of the speakers? Maybe for Safoura or Sarah, I guess.
Yeah, I think.
So Sarah, how do your predictions accuracy varies across, if you compare to level ground walking? Can you elaborate a little bit on that?
So for incline walking, it was very close to level walking because we're doing two simplification. One of them is you're just using one term, and the tangential ground reaction force and the angular acceleration term, we're not considering those terms. And in terms of this simplification, normal walking and incline walking were the same. So for both of them has about 97% contribution of the normal ground reaction force. So for these simplification, they were the same. For decline walking, the effect of tangential ground reaction force in the moment was higher due to the angles of walking and the geometry of walking. For the second simplification, which we are only taking the forefoot, that was actually for all of them, forefoot cause a plantarflexor effect on the reaction on the ankle. So that's the same. But where we assuming the moment arm of the forefoot is almost constant during the entire gait cycle to cancel out the effect of moment arm. That's another place where there is different. I also have additional a slide regarding that.
I think that will be great for the chat then later.
Oh, okay.
For the sake of time.
Yeah, okay. So for that, we evaluated the moment arm on different terrain, and we saw that for incline and level walking, the moment arm is almost moment arm is almost constant during the entire gait cycle. But for decline walking, there is a little bit change during the gait cycle, and by that simplification, we reduced the accuracy of the model in decline walking. But for incline and level walking, both of this simplification has the same effect, and finally, the model could estimate like 97% accuracy.
Thank you. I'll pass over the word to my co-host, Nidhi.
Great. So I think we got to most of the questions in the chat. If there are any questions we didn't answer, I encourage the speakers to answer them directly in the chat. Let's move on to the next session. So our first speaker in this next section is Richard Pimentel, and he's from the BME department, which is joint between NCSU and UNC Chapel Hill. And he's going to talk to us about novel clamp protocol examines cause-effect relations between propulsive force, walking speed, and cost of transport.
All right, thank you. Let's get right into it. So we all use propulsive force, or FP, to push our body forward while walking. This horizontal portion of your ground reaction force pushes our bodies forward. Peak FP declines with age and gait pathology, so investigating how FP affects walking speed and quantifying their effects on walking economy might help us better understand the decline of walking speed. So our purpose for this investigation was to investigate how FP governs the selection of walking speed and to quantify how prescribing walking speed, or FP, impacts walking economy. We took a different approach to tease out differences between walking speed and FP by using a self-paced treadmill. The self-paced mode used the average center of pressure from each side of a split belt treadmill, and we designated a dead zone in the center of the treadmill where walking speed wouldn't change when the average center of pressure position stayed within the dead zone. If the person walked faster and the average center of pressure moved in front of the dead zone, the treadmill would speed up, and vice versa for slowing down. Prior to our experimental trials, we ensured all participants were comfortable with increasing and decreasing the treadmill speed on command. For our protocol, we asked 20 healthy young adults to walk at 5 different speeds relative to their normal overground walking speed. All of these speed clamp trials were locked at a fixed speed for the duration of the trial. We measured their average peak propulsive force during each of the speed clamp trials, and then asked them to target that same FP in 5 more trials while walking in self-pace mode. During this FP clamp, participants could select their speed at will when targeting FP. So to summarize, we have 5 trials from the speed clamp, 5 matching trials from the FP clamp, which all were done for 5 minutes each, and then we averaged our primary outcome variables over the final 2 minutes, which were walking speed, peak FP, net metabolic cost, and cost of transport. So here's the relative FP from all participants across all speed clamp trials for the full 5 minutes. You can see that the average FP from the final 2 minutes matched the condition intensities. The relative FP during the FP clamp resulted in a similar distribution. And even after a minute or 2 of adjustments, the self-paced walking speed during the FP clamp also ended with similar relative intensity as the prescribed conditions. Now let's look at some correlations between our primary outcome variables. We found a strong relationship between walking speed and FP across both clamp types, with about 80% of variance explained between the 2 variables. Now we have correlations to walking speed on the top row and to FP on the bottom, with metabolic power in the middle column and cost of transport in the right column. Once again, the trend lines and correlation coefficients for both speed and FP clamps are highly similar across all plots, with about 54% of variance explained for net metabolic power and a weaker 17% for cost of transport. Now let's do a more direct comparison between the 2 clamps to see how participants fared during prescribed speeds versus prescribed FP. With the speed clamp in circles and the FP clamp in squares, you can see that they're pretty similar for the norm condition. And as we increase condition intensity, both walking speed and FP significantly increase from the norm condition. As we decrease condition intensity, both walking speed and FP significantly decrease as well. However, we also see a mismatch at the lowest condition intensity between speed and FP, where participants walked at the same FP, but at faster speeds during the FP clamp. Moving on to measures of walking economy, we now have net metabolic power on the left and cost of transport on the right. These outcomes were similar between clamps with the norm condition. And as we increase condition intensity, net metabolic power increases, but cost of transport only significantly differs from the norm condition at the highest intensity. As we decrease condition intensity, only the lowest condition intensity shows a significant difference from norm for net metabolic power. We also see another effect of the mismatch at the lowest condition intensity, where participants walked with higher net metabolic power during the FP clamp. So our findings build confidence that devices and therapies designed to enhance FP will result in faster walking speeds. And the mismatch at low intensities might explain self-pacing preferences or reveal a new training protocol to increase walking speed. Thanks a lot to my lab, my research participants, and the NIH for funding this study.
Thanks a lot, Ricky. So continue posting your questions in the chat and we'll get to them during the Q&A. Our next speaker is Abhishektha Boppana, and she's going to, and she's from University of Colorado, Boulder, and she's going to talk about statistical dynamic foot shape model.
Thanks for that introduction. So my name is Abhi Boppana. I'm a PhD student at CU Boulder. I'm presenting on our statistical dynamic foot shape model we've been developing. So we know that proper footwear fit is important in reducing injury and improving performance. However, some footwear designs inherently have improper dynamic fit, where proper fit isn't maintained during motion. A commonly reported dynamic fit issue in ski boots, snowboard boots, and spacesuit boots is heel lift, where essentially the foot lifts inside the boot during heel off, rather than the boot lifting off the ground. Since we know that foot shape is dynamic during gait, we were curious if we could model dynamic foot shape and use that model to inform footwear design for improved fit and comfort. So we collected dynamic foot shape data using our in-house custom 4D scanner. This scanner has 6 Intel RealSense depth cameras placed around a treadmill and calibrated to a single volume. These cameras capture point clouds of subjects' feet from heel strike to toe off at 90 frames per second. And we found they were accurate to about 2.5 millimeters using a post hoc analysis. We recruited and collected data from a total of 30 subjects for our study. And this is an example of one of the data captures from one of our subjects. You can see the compilation from all the cameras giving us a full 4D image of their feet. So to develop our foot shape model, we essentially took the raw foot scans and identified a single candidate heel strike to toe off frame, from which we now had a total of 1,771 frames or scans across all subjects. We then isolated the right foot from these scans, and then we went ahead and converted that point cloud into a mesh. Then we used a high quality foot scan from the University of Michigan, which is taken from a traditional laser foot scanner, and used that as a template to morph to all the frames that we had in our data set. This allows for any small holes in the scans that we collected to be filled and ensures that we have the identical number of vertices across all subject scans across our whole data set. Finally, we then did a principal component analysis on the array connecting all the vertices of all the scans across all subjects. And that gives us a shape modes for a statistical shape model. So here we are visualizing the first 8 shape modes or principal components of our model, which in total capture about 95% of the variance across all the scans. The variance here is represented as a transition from blue to red. You can see that in the first shape mode with 78% of total variance, we're capturing the gross motion of foot during gait. And also in the third shape mode, we're capturing changes in foot length as well. Then to develop a predictive component to our model, we use an elastic net regularization technique. From all the scans, we first calculated normalized ankle and MTP joint angles across all 3 anatomical planes. And then using that along with the demographic data and anthropometric data we collected from our subjects, those are fed in as predictors to our model, which is then trained to predict the values along the principal components or the shape nodes. We cross-validated our model using a leave one out method where one subject's data is left out and predicted with the model trained on the other subject's data. The resultant model is essentially, which is a parametric statistical foot shape model, starts with the mean foot shape, which has all the foot scans across all our subjects. And then the 8 shape modes each have a regression equation that was predicted from the elastic net regularization technique across all subjects. Those predicted shape mode values are then added to the mean foot shape as deformations along the shape modes, which gives us our predictive dynamic foot shape model. And that's able to predict the foot shape as we're changing both anthropometric and kinematic predictors, as you can see here in this little video. You can actually go play with this model yourself. We built a little web tool that you can go visit the URL here, and you'll be able to play around with the sliders yourself and visualize how that changes the foot shape. And we found that our final error was about 5.2 millimeters. And so finally, to translate this into boot design, we found the 5th shape mode particularly interesting as we capture variation in both the heel and the instep area. The blue to red transition along this shape mode essentially shows the loading of the foot during gait. So the blue shape mode is essentially the loaded foot during stance phase, and then the red is the unloaded shape. You can see there's quite a bit of difference in the heel and instep areas. So we know that instep area slightly correlates to, or instep height slightly correlates to foot length, but there's still some variation in instep height within subjects that we didn't capture in our study. But we believe that there is some sort of dynamic nature to the instep height changes because it correlates to the dynamic nature of the longitudinal arch. So we can see that when the instep height drops when it's loaded, there may be an opportunity for us to address heel lift in boots, but dynamically having some sort of lacing system or compressible upper that accommodates that shape change in the instep to go from the drop to the risen position. And so finally, I'd like to thank you for this opportunity to present. You can go play with our model at the link here or read more about the model itself in our recent published Journal of Biomechanics paper. And feel free to contact me over email. And of course, thank you to our collaborators in this project as well.
Thanks, Abhi. So yeah, continue posting your questions for Abhi in the chat. Our next speaker is Ryan Schroeder, and he's from University of Calgary, and he's going to talk about series elasticity does not eliminate the Series elasticity does not eliminate the need for active walk and running. Go ahead, Ryan.
Sure. Can you see the right side of the presentation okay?
Yes, we can.
Great. So anyone who's ever run a marathon knows that it takes a lot of energy to run. And in fact, the energy you consume per time increases substantially with running speed. Perhaps the most prolific model of running has been the spring mass model. But as a matter of fact, the spring mass model doesn't really have any clear sort of energetic costs, and so it can't really make good predictions about how that cost might change with something like speed. On the other end of the spectrum, more complex musculoskeletal models can be difficult to parse due to high dimensionality, and they also tend to have higher computational costs. So the question I'm asking here is, can we devise a simple model that can help explain our understanding of energy costs in running? So if I go back to the spring mass model, we have a point mass connected to a spring-like leg that compresses and extends during stance and launches the body into the air during the flight phase. This model does a pretty good job of producing things like ground reaction forces over time, fluctuations of power within the leg, and things like work loops as well. And so one of the things we find that given the spring mass model works without a muscle, you could attach a muscle in series to the spring, and it could operate isometrically and simply hold on to the spring without having to do any work and allowing the spring to do all the work. But as a result, we don't have any clear sense of where costs might come from since the model isn't doing any work. Empirically, at least in running turkeys, about 60% of the positive work per step comes from the elastic tendon. So this might seem like a, something that endorses this idea that passive elasticity is a dominant phenomenon in running. But this also means that there's a remaining 40% of that positive work coming from muscle shortening. And so the spring mass models just can't really explain this active muscle work, and thus can't explain the energetic costs coming from that work, which has been estimated to be about 3/4 of the total cost of running empirically. So again, the question is, can we develop a simple model that can explain active muscle work and energy costs resulting? So we start by adding parallel damping to the spring And this is basically just a simple way to model tendon hysteresis. And we also consider collision loss at the initial point of contact during stance. And then we add a series actuator that can extend and do active work on the system. For the actuator, we consider two primary costs. One is the work of the actuator, which we just simply think of as ATP from a cross-bridge cycle, for example. And then a second cost that mechanically we express as the rate of force production in the actuator. And we think this is related to the transport of calcium from the myoplasm to the sarcoplasmic reticulum. Specifically, recently there's been a lot of emerging evidence to show that high magnitude forces at rapid rates cost a meaningful amount of metabolic energy. And so this force rate is meant to represent that cost. When we run the model through a dynamic optimization, we ask what are the optimal way that the actuator can change its length over time to minimize these two costs per some prescribed step length, step frequency combination. In the top, we see the output of the model compared to what humans do on the bottom. And we can see that it does a reasonable job of producing ground reaction forces over time, power within the leg, and the work loop. So I'll just focus in on power because there's a lot to parse here. One of the things you can notice is that the actuator does a lot of positive work late in stance. And this is mostly to overcome passive dissipation in the form of the collision loss and hysteresis loss. But the actuator also does a little bit of negative work early in stance. And this is to help mitigate particularly spiky ground reaction forces and reduce some of that force rate cost. But I already told you that the spring mass can do a good job of producing mechanics. So we'll look at how the model does with cost. So this is energy cost per time as a function of running speed. And we can see that in humans, that cost increases with speed. And the model does a pretty reasonable job of capturing these increases. We can look at where the cost comes from in the model. For example, work to overcome collision loss and hysteresis loss, as well as the force rate costs. But most of the increase in costs with speed actually comes from increased collision loss at higher speeds. So despite the fact that the model does save a lot of energy by having a spring and utilizing a substantial amount of elastic return, active work still accounts for about 68% of the cost in the model. And this agrees reasonably well with empirical estimates. And this is despite the fact that only 5% of mechanical energy is lost in the system due to these passive dissipative elements. So the actuator does extra work in order to help reduce this force rate cost. And so more or less the model does a reasonable job of explaining these running energetics with these two relatively simple costs of work and force rate. Thank you.
Thanks, Ryan. Everyone continue posting questions for Ryan in the chat, and we will quickly move on to our next speaker, who is Kaylin Hirschman, and she is from University of Colorado Boulder, and she's going to talk about the effects of joint quasi stiffness on leg stiffness when running uphill or downhill.
All right. Is everyone seeing that okay?
It's a little pixelated, but why don't you continue? Maybe it'll get better.
Okay. Thanks for the introduction. Oh. Okay. Running specific leg prostheses acts as a biometric spring during level ground running, but this spring-like function may not mimic biological leg during running on slopes. Determining the contribution, joint stiffness to leg stiffness could improve assisted device design for running on slopes and level ground. However, biological legs have been characterized as linear springs with a stiffness equal to force divided by displacement, and the ankle, knee, and hip joints have been characterized as angular springs, stiffness equal to joint moment divided by angle. It's therefore important to relate angular joint stiffness to linear leg stiffness to calculate the contribution of the in-series ankle, knee, and hip joint springs. To do this, we used a novel equation derived by Nitton-Molkar. So in order to relate angular joint stiffness to linear leg stiffness, we need to go from angular units of measure, which are in italics, to linear units of measure in regular font. To calculate theoretical leg stiffness, Nitton used angular joint stiffness, which is donated by K, and the external moment arm of the joint in meters, which is donated by R, and is the perpendicular distance from the joint center of rotation to the ground reaction force vector. Now, running on slopes, stiffness during the first half of stance or the initial phase, and stiffness during the second half of stance or the final phase may be different. So we calculate the contribution to initial theoretical leg stiffness and final theoretical leg stiffness, which I'll explain more later on. So we aim to determine the contribution of the ankle, knee, and hip joint stiffness to theoretical leg stiffness, and hypothesized that when running uphill compared to level, ankle joint stiffness and hip joint stiffness during the second half of stance phase will contribute more to theoretical leg stiffness. And when running downhill compared to level, initial knee joint stiffness will contribute more to overall theoretical leg stiffness. So 20 runners ran on a forced treadmill at -6 and 0 degrees at 3 meters per second, +6 degrees at 2 meters per second. We simultaneously measured kinematics with a motion capture system, calculate joint angles and moments during ground contact using visual 3D. As I mentioned earlier, joint stiffness may change between the first and second half of the stance phase during slope running. So we calculated initial joint stiffness as the slope of the moment angle curve from 20% of peak moment to mid-stance. Final joint stiffness is the slope of the moment angle curve from mid-stance to 20% of peak moment. The measured angle at the ankle, knee, and hip are shown here. So to determine the contribution of the ankle, knee, and hip joint stiffness to theoretical leg stiffness, we rearranged the equation to equal 1. So each of the terms sums to 1 and represents the contribution of each joint stiffness to theoretical leg stiffness. So this figure displays the percent contribution of the ankle in circles, knee in squares, and hip in diamonds to theoretical leg stiffness during the initial phase of stance. Slope is on the x-axis and percent contribution is on the y. The numbers across the top of the graph in yellow boxes are the average theoretical leg stiffness values at each slope, and the asterisks indicate a difference from level ground. Compared to 0 degrees, the ankle's contribution to theoretical leg stiffness decreases at -6, but increases at +6 degrees. The knee's contribution increases at -6, but decreases at +6 degrees. And the hip's contribution to theoretical leg stiffness decreases at -6, but increases at +6 degrees. Now this figure displays the percent contribution of the ankle, knee, and hip to theoretical leg stiffness during the final phase of stance. Slope is on the x and percent contribution is on the y again. Compared to 0 degrees, the ankle's contribution to theoretical leg stiffness decreases at -6 degrees, but increases at +6. Knee's contribution to theoretical leg stiffness did not significantly change across slopes. Compared to 0 degrees, the hip's contribution increases at -6 degrees. So revisiting our hypotheses, we partially accept our first hypothesis because compared to level ground, final ankle stiffness did contribute more to theoretical leg stiffness, but final hip stiffness did not. We accept our second hypothesis. When running downhill compared to level ground, initial knee stiffness contributed more to theoretical leg stiffness. So in conclusion, when running uphill compared to level ground, the contribution of initial ankle and hip stiffness to leg stiffness increased, final ankle stiffness increased. Now, in thinking about assisted device design and taking theoretical leg stiffness into consideration, this could mean that when running uphill, an assisted device should be less stiff at the knee prior to mid-stance and less stiff after mid-stance at the ankle. And when running downhill compared to level ground, contribution of initial knee stiffness to leg stiffness increased, final ankle and hip stiffness increased. When thinking about assisted device design and taking theoretical leg stiffness into consideration, this could mean that when running downhill, an assisted device should be stiffer at the knee prior to mid-stance, stiffer after mid-stance at the hip. Thanks for listening.
Thank you. So I guess that was our last speaker in the session. I'm going to hand it over to the other two moderators for the Q&A.
So our first question is going to go to Ricky. It's a question by Peter Adamczyk. Step length remains as a free parameter for gait here in your paradigm. Did or would differences in the parameter explain the discrepancy between speed and FP?
Yes, as I said in the chat, we haven't looked at step kinematics yet. We do have that data. We're really excited to analyze it this fall. I would think that the step lengths and step kinematics would associate quite well with walking speed. But as I showed at the mismatch with the low intensity condition, there's definitely other stuff going on there, and we're excited to see the response.
Thank you. My next question is going to be for Abhi on foot models. That's very exciting work, I think, with the modeling of these different feet in dynamic situations. You reported a root mean square error of 5.2 millimeters, which do you know if that occurred in all dimensions, and what would be the critical areas of the foot for the modeling that you see those changes, and how would you implement that into shoe design?
Yeah,
that kind of matches a full shoe size if I take it as a direct translation.
Yeah, that's a great question. I think it really depends on the application you want to apply the model to. So for us, like we were very interested in looking at that in-step step changes because we want to kind of develop some new lacing techniques that accommodate those. I don't believe we did an analysis on where exactly that error is, greatest versus least. We found that just kind of overall, it seemed to be pretty even. There was definitely a bit more error around the edges of the model. So around the sole, we actually did not really capture the sole with our cameras because we didn't have a see-through treadmill, but that's where I found the most errors, but we weren't too concerned with that. Everywhere else, kind of the upper part of the foot seemed to be pretty consistent in the 5.2 millimeters. But yeah, I think it's really interesting to see how people apply this model and like how to use those different changes for sure.
Great. And I also saw you posted the link of your model in the chat. So I encourage everybody to explore. Yeah, I'll turn the word over to Jaimie for the next part of questions. Thank you.
Thank you. Yeah, I admit I already clicked the link and I've been playing around with it. So very cool. All right. So our next question is for Heidi from Kota Takahashi. He asked, why do you think D-mama decreases with faster walking? Apologies if I misread the graph. It seems like the ankle moment would increase with faster speed. So why would the moment arm decrease?
I think I might have responded to this earlier. But yeah, we think that it's due to the fact that the ankle is trying to like slow the I might be saying it backwards, slow the body down.
Yeah, you totally did. I'm so sorry. I'm on the wrong number. So apologies, everybody. I meant to ask Caitlin a question, actually. Heidi, thanks for calling me out, but in a super nice way. Sorry, Caitlin. I had a list of questions for you actually too. So I'm going to ask Caitlin actually about the downhill running. For me, we've experimented with downhill running on our treadmill in the lab before, and it feels very different than running over ground like downhill. So can you talk more about your expectations for how your work will translate to over?
Yeah, that's a good question. Yeah, I think with the treadmill, it's not only different from outside, like feeling wise, but also, you know, running over ground, you might be, you know, some perturbations with rocks and stuff. I've actually not ran downhill very much myself on a treadmill, but I do, when I have, I almost feel like I'm having to brake a little bit more to kind of not overrun the treadmill, almost kind of like sit back a little more. God, in terms of how it might apply, I suppose it might, we might see like less knee joint stiffness when running outside because of that, maybe not having to feel like you're braking as much and letting your legs kind of run a little bit more when you're running outside. But that's a good question. I'll have to think more about it.
Thank you. We can chat more in spatial chat too about it.
Yeah, that would be great.
Yeah, sounds good. Ryan, I saw that you already answered this, but from Wooter, he's asking what happens beyond 4 meters per second. So can you kind of elaborate on, or just kind of tell those who didn't see the chat response with your model?
Sure. So the answer I gave was more or less the trends that we saw over the range of speeds I showed continue. So you continue to see more dissipation at higher speeds and thus more work cost. Force rate cost also continues to go up. And this is because Stance time is slightly decreasing as it does in humans as well. And peak forces as a result also increase slightly. So basically everything kind of just chugs along at higher speeds.
Okay, can I kind of ask a follow-up to that, I guess, in terms of like the swing leg and what you think that does at higher speeds as well?
Yeah, well, certainly based on experiments with Dokay on metabolic cost of swinging the leg, given the frequency dependence, and we know that frequency increases at higher speeds, you'd have to expect that cost of swinging the leg would also increase. Although I should note, I think there's perhaps an underappreciated connection between the collision loss and the swing leg. I didn't mention this, but in our model, the speed of the foot, the amount of momentum lost by the collision loss, we just assume that the foot is moving at the same speed as the center of mass, because we don't, of course, have those dynamics built into the model. But of course, you have some control over the speed of your foot when you land on the ground. But presumably, if you're doing work to slow the foot down before it lands on the ground and thus reduce a collision loss, then presumably that would come at an increased swing leg cost. So I think those two are kind of a little bit related, and we might be encapsulating some of the swing leg cost in our collision loss in the model.
Great, thank you all. And I'll turn it back to Caroline actually to introduce our next set of speakers.
So we have another lineup of 4 more speakers for the session for the last block. And the next speaker up will be Zachary Mercer from the Florida State University. And he'll be presenting on a systematic study of reduced order physiological bouncing model with trajectory optimization. Zachary, the floor is yours.
All right, how's it look so far?
Very good.
Okay, awesome. Well, thank you for the introduction. My name is Zach Mercer. I'm a researcher at the Alternative Robotics Laboratory in Tallahassee, Florida. And this is my research, a systematic study of reduced order physiological bouncing models. Well, so what are we interested in? We want to rapidly predict human movement. Specifically, we're interested in how that movement changes or adapts in the presence of external forcings, such as exoskeletons. If we're able to predict how a device can influence our behavior, we believe that we can find an optimal control plan allowing these devices to best augment human movement. Now, that might sound familiar because there's already some practices doing this, notably human-in-the-loop optimization. This is a really effective process because it's using this real-time human data to drive this exoskeleton tuning and control. Now, this can take anywhere between 10 minutes to a couple hours to converge to this optimal control pattern. And we're hoping that we may be able to make this into a faster process. Now, the way we want to go about that is through this creation of simple physiological and behavior models. Now, with all the dynamics of this locomotive model and some sort of performance criteria, say minimizing metabolic cost, we have all the ingredients we need for a simple or for a fast to compute trajectory optimization problem. Now, this gives us a very simple and predictive approximation of human dynamics and how we can optimize the associating actuators. But we need to start with the foundation. We need to start with something simple and a very simple task, such as human bouncing. Now, what's so nice about human bouncing is the majority of the movement is powered by a single MTU, notably the plantarflexors. So we devised a very simple 2D planar model that captures the majority of these dynamics. So now that we have those dynamics and constraints in place, we give it some sort of objective, something that needs to minimize for a performance criteria of this movement. We try out 4 different objective functions, force-based and mechanical-based, hopefully good proxies for minimizing metabolic energy. What's more, this simple model allows us to investigate several kinds of muscle models. We can start with the simplest one, just a contractile element, just a simple actuator. If we add some series elasticity, how does that change the movement? Maybe we add some elasticity to the contractile element. Finally, we can move forward with a full-blown hill-type model and see what patterns of human behavior emerge from these optimizations. And that's exactly what we ran. We ran a bunch of these. You can see on the far left column, these are all the muscle models we used. On the top row, those are the objective functions we solve for. Now, each one of these cases is bouncing frequencies between 1.5 and 4 hertz. Overall, this is just under 2,500 simulations. Each one took a little less than 10 seconds to solve for. So now we can see how these might compare to actual human bouncing. And what we know from human bouncing is there's a frequency we prefer. So those cases which did not find this this preferred bouncing frequency are not very good models of a human bouncing task. However, some got pretty close, notably the hill type model minimizing for these force-based objectives. What's more, we know that the phasing between the muscle and the MTU as far as their cyclical length changes, it changes around that minimally energetic frequency. Now, these mechanical-based models, the models that were able to find a preferred bouncing frequency, solving for these mechanical-based objectives, were able to capture some of these trends. Most notably, the hill type model, solving for these mechanical-based objectives, had the least amount of movement of the contractile element, effectively isometric, for this minimally energetic frequency. Now that we have this simple framework built out, it allows a lot of kind of plug and play for more investigation. If we change the parameters of this model, say we increase the mass a little bit, how is that going to affect what this minimally energetic frequency looks like? We can use more sophisticated objective functions, such as active muscle volume, and see if human data, if that compares to human data, to what extent, maybe it does better, maybe it does worse. We can add extra dynamics, such as activation, deactivation dynamics between the neural control and the force output of the actual MTU. Moreover, we can try hybrids of these objectives. Maybe we're optimizing for 60% mechanical power, 40% force-based work. We can investigate all these pretty rapidly and pretty quickly through this trajectory optimization technique. So in conclusion, trajectory optimization with these very simple models is able to capture these key trends of real human bouncing as a function of frequency. This allows for these very, I'm using the word rapid a lot, but these rapid plug and play experimental simulations and investigations. Currently, we're collaborating with the University of California, Irvine Neuromechanics Laboratory and Georgia Institute of Technology's Power Laboratory for more of a direct comparative analysis against human movement. Thank you for your time. I'm looking forward to any questions.
Thank you very much for this excellent talk, Zach. Our next speaker up will be Jake Hinkle-Lipsker, and he's from the University of California State University, and he'll be speaking on Watch Your Step, altered spatio-temporal strategies while navigating unexpected obstacles under physical fatigue.
Hello, everyone. You can see my screen?
Yes, thanks. Take it away.
My name is Jake Hinkle-Lipsker. I'm presenting this on behalf of my graduate student, Michael Weiss, who was unable to be here today, so I'll do my best to be his substitute. So as a little bit of a background, physically demanding occupations, such as firefighting in the picture on the right, as you see, requires a complex level of environmental navigation, often over rough terrain, and that can often get compounded by other things like physical fatigue, wearing heavy PPE, maybe occlusion of visual perception by smoke. So it naturally follows that one of the main causes of injuries in firefighters is slips, trips, and falls, or musculoskeletal injuries that arise from that, even more so than things you might traditionally think like smoke inhalation or burns. What we do know is that across a variety of different tasks, fatigue tends to impact visual perception and attentional processes in a negative way. But what we don't know is if there's some sort of relationship between how fatigued you are and how well you're able to make your way through your environment during the performance of job-related tasks. So in our study, what we sought to do was investigate how physical fatigue impacts one's ability to negotiate unexpected and randomly located obstacles during locomotion. And beyond that, we also sought to determine whether that was somehow related to an individual. So using a series of regression models, we looked to seek how well things like age, sex, height, and estimated VO2 max predict spatiotemporal obstacle negotiation parameters. So hopefully this video plays okay. But what we did was we designed an experiment where somebody had to walk through a darkened lab. And once they got within a meter of an obstacle, it would appear in their path. This obstacle was moved to a random location between each trial. So participants could not predict where exactly it was. And so again, as they walk, you can see they're in a completely pitch black lab. And then once they reach the 1 meter threshold, a motion sensing light triggers and the obstacle becomes illuminated. And this requires like a rapid visual perception process. We also included one sham trial in there where there was no obstacle and they just sort of walked freely through the space and didn't encounter one. So the general overview of the study, we recruited young, healthy participants, tried to replicate maybe a sample of a blue-collar working population. And they completed 10 familiarization trials to get practice in and to hopefully mitigate any effective learning. And then completed 5 obstacle negotiation trials, as you just saw in the video there. They then underwent a fatiguing protocol and immediately after this did 5 more obstacle negotiation trials in their fatigued state. The fatigue protocol itself consisted of an anaerobic component and an aerobic component. It lasted about 35 minutes in total, and I can pretty confidently say it was very challenging. I think the number was like 38% of all, only 38% made it all the way through before having to drop out due to exhaustion. So we did find some interesting results. One thing we found was that following the fatiguing exercise, people exhibited significantly decreased leading toe clearance as well as increased leading heel clearance, which maybe indicates some level of plantar flexion on the leading foot, as well as decreased trailing heel clearance. So they exhibited riskier behaviors, which was somewhat interesting because we thought that it might have gone in the other direction where people would adopt a more conservative approach following fatiguing exercise like you would see in maybe an older adult. What we also found was that fatigue led to significantly decreased leading and trailing foot placement on the step prior to obstacle negotiation. Foot placement is a pretty crucial variable in controlling the trajectory of the foot once it enters swing phase, where a longer foot placement away from the obstacle in the horizontal direction gives you more time essentially to control the trajectory of the foot as it clears the obstacle. And so again, when fatigued, people are actually stepping closer to the obstacle. Interestingly, what we also found was through a series of regression models that estimated VO2 max predicts these foot placement parameters that I showed you on the previous slide. So essentially what this is showing is that a higher level of cardiovascular fitness when physically fatigued means that people will place their foot further away from the obstacle. So perhaps being more fit allows for somebody to maybe mitigate the effects of fatigue and still adopt a safe obstacle negotiation strategy. And this was accompanied by a moderately strong R-squared value as well. So in summary, young healthy walkers tend to exhibit more risky obstacle negotiation behavior when fatigued, which again, sort of goes against our hypothesis. And this was shown through lower clearance values as well as a shorter foot placement to the obstacle. And just to reiterate, previous work has determined that maybe a further foot placement from the obstacle allows for people more time to control the trajectory of their limb once it enters swing phase. We also found that VO2 max was a significant predictor of leading and trailing horizontal foot placement. So more physically fit individuals place their foot further away from the obstacle on the step immediately prior to obstacle clearance. And that maybe doesn't come as a surprise, and I'm maybe somewhat preaching to the choir, but essentially if you are doing a activity that requires obstacle negotiation safety, it probably helps that you have a high level of physical fitness. So sort of moving forward, what we're looking into is more of the mechanistic aspects of how this is happening. So are these altered strategies the result of impaired motor behavior or perhaps sensory behavior or both? So we're delving into maybe more of the coordination aspects of how people are negotiating obstacles under fatigue. On the sensory behavior side, a little bit of a spoiler alert, but it turns out there are some differences in gaze dynamics as a result of fatigue, which may also help to further explain these results. And I'll sort of leave that as a teaser for another student of mine, Maria Ayala, who's presenting at the poster session immediately following this on that stuff. So thank you all for your time, and I look forward to answering any questions you may have.
Thank you very much, Jake, and also for the plug for the next poster. Very interesting work. The next presentation will be by Emily McCain from North Carolina State University on the impact of reduced gait asymmetry on knee joint reaction forces.
Hello all, can you hear me and see my screen?
Yes, thank you.
Okay, great. My name is Emily McCain. I just finished defending my PhD in June, and now I'm at the Center for the Intrepid working on some new research. So I have a quick disclaimer, as well as a list of author affiliations, and then we'll get into the background. So chronic injury or disease-induced gait deviations may precipitate changes in joint reaction forces that contribute to increased incidence of osteoarthritis as well as joint pain in clinical populations. Specifically, we think it's possible that unilateral impairment of a joint or limb may inhibit ipsilateral cushioning during heel strike and result in increased limb and joint loading. Now, while concurrent anatomical or physiological changes make isolating the impact of reduced impaired limb cushioning on joint reaction forces difficult in clinical populations, our previous research has demonstrated that bracing can be used to limit lower limb joints and restrict joint motion, and even impose clinically relevant gait deviations in unimpaired participants. So for this research, we extended previous work by using an EMG-informed musculoskeletal simulation to determine the impact of unilateral joint restrictions on calculated joint reaction forces. More specifically, we simulated previously collected data from unimpaired participants that walked with ankle restriction, knee restriction, and simultaneous ankle and knee restriction. And we compared these conditions to a restricted condition, to an unrestricted condition, excuse me, where bracing was worn but not restrictive, to see how the reduced range of motion at a joint might impact ipsilateral limb and joint loading during heel strike. We scaled personalized models according to measured user anthropometry, and we used experimentally determined kinematics, ground reaction forces, and muscle constraints determined from measured EMG recordings to be input into the computed muscle control algorithm along with our personalized musculoskeletal models. Lastly, we included a joint analysis probe as well as a muscle analysis probe to determine reaction force at the joint along the line of action as the bone. Because we anticipated that changes in limb loading would impact joint reaction forces, as a proof of concept, we first looked at how our imposed joint restrictions impacted limb loading. Specifically, we looked at peak limb loading as well as limb loading rate. We found that with knee restriction, that our limb loading values increased significantly ipsilaterally, suggesting that limiting knee joint motion does reduce ipsilateral cushioning and the limb's ability to yield to an impulse load. However, increases in limb loading did not result in larger joint reaction force peak or loading rates. We didn't see any significant change at the ankle or at the hip. And the only significant change we found was at the knee, where we found peak knee joint reaction force actually decreased significantly with ankle restriction, notably the opposite of what we hypothesized. So given that changes or increases, in limb loading didn't result in increased joint reaction forces, we next looked at the muscle forces around each joint. Specifically, we summed time-varying muscle forces across the ankle, knee, and hip during loading response, and then integrated with time to approximate muscle contribution to joint reaction forces at the ankle, knee, and hip. Ipsilateral reduction in muscle force may explain why joint reaction forces were relatively unchanged despite increased limb loading relative to the unrestricted condition. Because while limb loading increased with knee restriction, we actually see that ankle, knee, and hip joint muscle forces decrease, appearing to offset the net joint reaction force values. And these results have broader impacts for rehabilitative efforts that are working towards joint loading reductions, because if muscle force contributions can offset changes in limb loading, then limb loading metrics might not always be an appropriate proxy for joint reaction forces in general. To sum it up, we found that joint restriction increased limb loading ipsilaterally, supporting the rationale that limited joint motion restricts the limb's ability to yield to impulse load. We didn't see that our changes in limb loading affected joint reaction forces as we anticipated. Instead, it seemed that reductions in muscle forces during loading response with joint restriction offset the changes in limb loading, so that we saw really similar joint reaction forces across conditions. So with that, thank you so much for the opportunity to present, and I look forward to answering any questions.
Thank you very much, Emily. Please, everyone, remember to post your questions in the chat, and we'll get to that in a moment. We are ready for our final speaker, Francie Wade from the University of Florida, and she will be speaking on the kinematic changes prior to and following walking speed transitions.
Helps if I unmute myself. Thank you. So the data that I'm presenting today is part of a much larger study ongoing that's funded by the NIH called the Mind and Motion Study. So why do we care about transitioning between walking speeds? It's something that we do in daily life, whether we're out in the mall, in the grocery store, crossing a street, trying to avoid a dog in a park. It's just a natural part of daily life outside of the home. But saying that, it hasn't received a huge amount of attention in the literature. In fact, if you look at speed transitions, most of the research tends to be on the walk to run transition, which, while important for runners, is not something older adults particularly are doing on a daily basis. So we wanted to investigate the changes in walking speeds, transferring from your preferred natural speed to either faster or slower walking. And we did this in a cohort of young and older adults. They started walking at their preferred speed and then either sped up or slowed down, as you can see here. We defined gait cycles from center of mass velocity. So we have forward center of mass velocity traced here. We defined a range where the speed changed, and then the peak or trough, if we were speeding up, prior to that speed change was considered the transition point. And then from this point, gait cycles were either defined as pre-transition or post-gait cycles. And so we looked at both younger and older adults, and also pre, during, and post for a variety of spatiotemporals and joint angles. So for normal to slow, these graphs just show all the adults grouped together. So young and old are in here for the, just to try and save time. Because interestingly, there weren't many age differences. In fact, out of all of the variables that we looked at, double support time was the only one where there were any age differences. And so older adults had significantly longer double support time than younger adults. But otherwise, the patterns of pre, during, and post gait cycles were very similar across age groups. So we can see that, maybe as expected, center of mass velocity and cadence and step length all kind of follow this nice step down trajectory, with blue being pre, orange being during, and gray being post. Interestingly, double support time seems to not differ pre and during, but then will increase post when transitioning to slower walking speeds. And stride length seems to have this kind of U-shape approach here, where the during is different to both pre and post. Step width was not affected in any ways. When we looked at increasing speed, we see a similar story with center of mass velocity, cadence, and step length showing a linear increase, whereas double support time, again, pre and during don't change, but post is different. And here we see stride length seems to differ during compared to pre but not post. Again, step width did not change. We also looked at stance limb joint angles during stance, and in general, the peak joint angles didn't vary much. You can see some of the differences here. The only one where older adults were different from younger adults was in dorsiflexion in the normal to slow conditions. But this is sort of preliminary data, and we would like to look at some of the propulsive and braking forces in the control of this, and that is definitely a future direction for this work. And also to investigate how older adults who may be at risk of falling or with movement disorder populations, how they may differ their changes in gait speeds and how this can impact them outside of the home long term. Thanks.
Thank you very much, Frankie. I will turn over the word now to Jaimie for the Q&A round for the last block.
Yes, and I know people are going to have to run soon, but we'll try to get at least each speaker a question here. So Zach, actually, Nidhi had a question for you, and she wanted to know, how does one know if the error in match of prediction is because of the muscle model or the objective function? And how much data or statistical power would you need to answer that question?
Let me think. I think it would be pretty difficult to tell unless you do a study, you know, taking one of them out and kind of doing a sensitivity analysis of it. So I've kind of embarrassingly, I've not really considered that too much, so I don't have a direct answer for it now. But doing some sort of sensitivity analysis, checking how it affects that resulting behavior would be the way I would go about it.
Great, thank you. Next question is for Jake from Loubna Baroudi. Really nice work and nice presentation. I was wondering if there was any measure of the fatigue level after the fatiguing trial, since some people did not complete your whole trial.
Yeah, that's a good question. So we, two things. So they did have a heart rate monitor on the entire time. And also there were subjective measures of fatigue taken throughout the fatiguing protocol, like RPE. I don't have the numbers directly in front of me. I can dig them up for you later if you'd like, but I think it was something, or there was something around the lines of like 180 beats per minute when they finished. And for the people who stopped early, they had like a reported RPE, like close to 19 or 20. So they were very fatigued. And then even following the 5 obstacle crossing trials, when they were fatigued, so which was probably a matter of like 5-ish minutes later, they still had a very elevated heart rate in RPE. So good question. And again, I can dig the numbers up for you if you want to chat later.
Thanks, Jake. I know Jake had a few questions in the chat too. So hopefully y'all can stop by. Yeah, y'all, I'm from Alabama, sorry. So if y'all can stop by in the spatial chat, let's talk more. Last question I have is for Frankie. And Frankie, I guess like there's this theme that we've had at ASB, right, with like indoor and outdoor and going outside of the lab. So do you think, you know, that maybe like a more real world environment could have impacted your results differently than what you observed? And then I'm going to throw another one at you too that has kind of come up in discussion, which is, you know, that I think it seems like a lot of our older adult populations that tend to be rather fit. And so I don't know if you could comment on your general population that was used in the study and how fit they were.
Sure, I think both great questions and points. I would love to do this outside. We're still figuring out logistics of that. We have an ongoing project that is looking at IMU data in and outside of the lab. And hopefully once we've validated some of that, we'll be able to do this in more real world situations. Because yeah, that's the white coat effect, right? And doing things in the lab is going to alter gait, and I'm not sure how much, because when I was looking at the literature, I couldn't find much on this in terms of just walking between speeds. So I think there's a lot to delve into in this area. And then in terms of the fitness of our participants, as I mentioned, this is part of a much larger study, and we have younger adults who are between 18 and 25, and then we have healthy older adults, and I'm trying to avoid using the word healthy, typical older adults who are over the age of 70 and have a score greater than 10 on the SPPB, and they are able to walk 400 meters in under a set amount of time that I can't remember off the top of my head right now. And then we have frail older adults who were not part of this data that I presented here. So they are separated. These are our like not at risk of falling older adults, I guess could be another way of thinking of it.
Great, thank you. So I'll invite everybody over to the spatial chat room, log in with your name, and we will be in room S2 Mari, and you can also search for people in spatial chat. Thanks everyone. Thanks to my awesome co-moderators too, and happy Friday.